So welcome to the second part of my talk. And as I promised today, I want to talk, you have seen already difference rings yesterday. So I showed them to you carefully that you get used to the notions. Now I want to show you a little bit more details, give some more insight about what I'm doing. Let me say there is quite some work on which this is based. So Abramov is one of the big heroes that is pushing that forward, what I'm doing. Michael Carr was a key player, the starting point of my work. Manuel Bronstein, Marco Petkoschek, Michael Singer, they were all influencing a lot what I'm doing. Also Frédéric Jussac and others are influenced me, but this comes in the third part. I will talk a little bit more. But here, and there are more, but this is basically what I say, this is the key where I try to incorporate things. So let's start slowly, and I repeat with the example to sum over the case harmonic numbers, but now I want to give you some more details about that. So the main issue is that I want to tackle the whole problem in a formal ring. Formal ring means a field, and then I join variables. So in the computer algebra setting. So you have seen this already yesterday. So I start with rational numbers, for instance. Then I join a variable x. It's transcendental over q, so it fields a rational function field. We have polynomials in the numerator and denominator. And I introduce also a variable s to model the case harmonic numbers. This is a polynomial ring, again, algebraic independent over the field of rational functions. Now, what was missing yesterday is that I have to say how these variables are linked to the sequences, so how they are evaluated. So what I have to introduce is basically an evaluation function, not in the mathematical sense, how you know, but really to evaluate an object, okay? And I start with how we can evaluate rational functions. In this case, it's obvious in a polynomial in one variable has only finitely many roots. So there can be only finitely many poles in the denominator, okay? So whenever there is no pole, then I just evaluate the polynomials and carry out the operation. If there's a pole, and there are only finitely many, then I could select a distinguished element to say this is a pole element. I make life easier, I just send it to 0. So because then I map basically the evaluation function to the rational numbers. I don't know anymore where the poles are, so one has to be careful for the evaluation that one always handles the poles. From which point on there are no poles anymore. This is important, okay? Okay, so we know now basically how to evaluate rational functions, and these are the called rational sequences that I can produce in this way. Now I join, now you see we are in this ring here, we join also the variable s, and I have to say now how the evaluation function acts on this extended ring. And we know the variable s should reflect the harmonic numbers. So the evaluation of s at a point n should be exactly the nth harmonic number. So n equals 1, s of 1 should be 1, for instance, okay? S of 2 should be 1 plus 1/2. This should be 3/2, okay? And so on. But that already tells us completely how we should naturally extend this map. So if we take a polynomial, the fi's are elements from these rational functions, then we evaluate, and we try to evaluate like a homomorphism. So we carry over the evaluation map to the elements. So the coefficients are rational functions. I have defined already how to evaluate them, so I use that map. And well, the harmonic number s will be evaluated as a harmonic numbers, and if it's raised to a power I, well, then I take this value to the power I. Okay? I call this now an eval ring, not an evaluation ring. Unfortunately, this notion is already used in maths. This would be the most natural setting, so I dare to say it now, eval ring. Okay? Good. Now we can extend this, so we can now go from, I want to make this clear. We can now extend this further. So we can go from tau, goes from A first to the sequences, and we take an element and map it now to eval fn, and consider the corresponding sequence at n equals 0, 1, 2, 3, 4, so I get the sequence. Okay? And this is, well, this is a function, and it's almost a ring homomorphism, but it's not an homomorphism. So let's look at that. Here's a counterexample. Let's take tau of x and tau of 1 over x. Well, I evaluate x, this is 0, 1, 2, 3, 4, 5. If I evaluate 1 over x, well, it's 0, I have a pole, 1 divided by 0, so the convention is I map it to 0, and then I get 1, 1/2, 1/3, and so on. Now in the ring of sequences, I have component-wise addition and multiplication, so this is my ring, so I don't work with Cauchy multiplication, but with Hadamard multiplication. So if I do that, I get the elements 0, 1, 1, 1, 1, 1, 1, okay? And that's almost the 1, 1, 1, 1 sequence, which should be, for if it's an homomorphism, tau of 1 should be mapped to the 1 sequence, right? And that's tau of x divided by 1 over x. So it's almost a ring homomorphism, only the first entry here is wrong. Yeah?
Could we, like, what if we change the convention and take infinity instead of 0 for 1 over 0?
Yeah, but one has still to do something. So that, but it goes in the same direction, what you suggest. I introduce now an equivalence relation. This is a common way how to do it with sequences. I say two sequences are equivalent if they agree from a certain point on. So there might be chunk in the beginning coming from poles, finitely many, but from a certain point on they agree. Okay? This is an equivalence relation. You can factor it out, and then you see you get again a ring back. It's again with multiplication, addition, as you know. And for simplicity, I don't work with equivalence classes. I just use again as I work with sequences, okay? But actually they're equivalence classes. And then suddenly we can see here that these two sequences are now the same because the first entry is wrong. So in this equivalence, there is the same equivalence class, okay? And in this way, the whole thing turns now to a ring homomorphism. Okay. So if I do that, factor out here, then I get a ring homomorphism, really. It's even better. It's an injective ring homomorphism. If I want to show it like that, it's not so obvious to see that it's injective. There's a summation theory behind, inspired also by Michael Singer, and that follows in a second or in some minutes, okay? But in the moment I say it's injective. And you can verify this algorithmically, okay? So now we have this, I know how to evaluate objects. Now, as you have seen yesterday, I also need a shift operator to model the shift. So I introduce now a ring automorphism, and for the rational functions, well, if I take a rational function, I replace x by x plus 1, just a substitution. This is my shift operation. And well, as you see, the nth harmonic numbers shifted are the nth harmonic numbers plus 1 over n plus 1, okay? So this shift, as I have done also yesterday, I introduce now the automorphism where s should be mapped to s plus 1 over x plus 1. And this can be naturally carried over. I have here now a polynomial. And again, this should be an automorphism, so I carry it over to all of the elements. The coefficients are mapped, these are rational functions. I know already how to map. And s is mapped to s plus 1 over x plus 1. Okay, so this is my automorphism. So basically saying this x goes to x plus 1 and s goes to s plus 1 over x plus 1, I have uniquely determined my automorphism. The rational numbers are kept fixed. This is automatically granted. And this A together with the automorphism, this is called a difference ring. It's one of the most simplest definitions that I know, and it's one of the most hairy things if you want to do then algorithms. the Leibniz rule with differential operator has more structure because it's not such, you see more the structure behind if you act on it. And the set of constants is defined like that. These are all elements which are kept invariant that you have also seen already yesterday. Yes?
I'm sorry, I must have missed something, but why is S sent to S with 1 over X?
Well, you see, we have, if I apply the shift operator to S1 of n, then this is k goes from 1 to n plus 1, 1 over k. And that's k goes from 1 to n, 1 over k plus 1 over n plus 1. Okay? So I want to model the shift acting on the object like acting on the variable. It should reflect the same thing. But there's still an important thing to glue things together. So there's still something missing. First, a remark. This is a set of constants. And in this case, well, if you have a ring, it's a subring of our difference ring. And in this particular instance, we are even better. The set of constants do not depend on the variable x and s. Okay, so the constants are only the rational numbers. So actually, it's a field, and I call it the constant field. Okay, and I will take care. Later, you will see I introduce several variables. Whenever I see a sum or a product, I will introduce variables. But I will take care that I never extend the set of constants. So if I start with a field, it will stay always a field. I will never go to the ring case because it's a starting point where it's a field. And I start with the rational numbers here. This is a field, and I do a tower of extensions, but I never extend the field set of constants. So the base field where I start is the constant field. And this is a special case of an R pi sigma ring. And well, if I would consider the rational function case like that, and I do the quotient field here, then this would be a pi sigma field in the Michael Carr sense. Okay? That's the reason why I also call it pi sigma ring. It's a ring, and the R will pop up later. You don't see it in the moment. And I will also explain the pi and the sigma in more details. Okay. Now, there's another important thing, and this makes the whole thing interesting. The evaluation function and the automorphism, they interact. So namely, more precisely, you shift formally, and then you evaluate at the point n. That's the same. Well, you carry out the shift sigma of s. You get s plus 1 over x plus 1. If you want to evaluate that, these are the n-harmonic numbers plus 1 over n plus 1. And that's exactly the evaluation of s at the point n plus 1. Okay? So the evaluation function and the shift interact, how they should interact. And now I can go back to my map here. If I shift formally, and then I consider the sequence, I get that sequence. That's the same as if I shift the sequence, and that's the same, I first go to the ring of sequences, and then I shift. So there's an interaction between tau and sigma. And that implies I can shift, I have here my formal ring, and I can shift back and forward. I can shift in one direction, can go shift backwards, and I can shift in the ring of sequences, shift the sequence to the left or to the right. Okay? And there is an injective map going from here to here. So I could either carry out operations here, or I could carry out operations in the image. And there's a one-to-one correspondence. And this diagram commutes. Okay? Or in other words, this formal difference ring, where I love to work, here all my algorithms work here, this is isomorphic to the image, namely the rational sequences adjoined with the nth harmonic numbers. Okay? So you have the sequence of nth harmonic numbers, you adjoin them to the ring of rational sequences. You get here a difference ring. It's a sub-difference ring of the ring of sequences. And this guy, two things are isomorphic. And that's a cool thing, because here, well, this is somehow an infinite object, okay? Whereas here, this is, I have one object, a polynomial, and that represents a sequence. And there's a one-to-one correspondence. That makes the whole machinery that I have so strong that there is, I can go in both directions, and whenever I have a solution here, I have it here, and if I have a solution here, I have it here. And I can go in both directions. Okay. And using that, I can now repeat what I did yesterday. I'm interested, I'm giving the right hand, the summand here, this is a sequence, and I'm interested to find a sequence in this image such that the telescoping equation holds. Well, and since we have here this isomorphism, this is equivalent to ask, does there exist a G? And if I'm given that G, I can compute this G, I will show you in a minute. Then I can translate this back, and the evaluation homomorphism, this eval function, gives me exactly the justification that I can go backwards. And by that, I get this evaluation. In addition, I haven't told you this, I can do bookkeeping where the poles are, and I know exactly from which point on the eval really agrees. This is important because this ring, I throw away the bad guys, and I need an extra function which tells me from which point on this problem is gone. And then I can really say from the lambda on, the output is the same as the input. This one has to do the bookkeeping. This is important. This is very convenient for the theory, and to say you have an embedding of different rings, but for summation you have to know the starting point where the eval really agrees. Okay, and having that, we get the closed form. Now, let me give you some more details how I can solve this. So I want to find an element in this formal ring such that this difference equation holds. So the first thing what one has to do is one has to degree bounds. One has to bound how big the degree can be of the solution. So we have to find a B with the following property. Whenever there's a solution of my equation, my telescoping equation, the solution should be bounded in the degree by B. So it should be the worst case how big the degree can be of my polynomial solution. Okay? And in this particular case, it's B equal 2. So there are algorithms which can allow you to compute it. In this case, it's very easy. If you look here, you have degree 1, and the theory tells me the summation variable in S can be at most 1 degree higher than the right-hand side. So it's 1 plus 1 is 2. Okay? But you need, in order to prove this, we need that the constants are the rational numbers. If the constants depend on x or maybe even on s, the degree bounds can be arbitrarily high, because a constant is a constant you can sneak in the solution, and then you can make it also the constant power to the 5, put it into our equation, and you have no control. So the constants must be fixed, must be free of x and s to get a degree bound. That's very, very important. Otherwise, I'm lost. I don't know how to do it. Okay, but now, knowing that, if there's a solution, it has this shape. Okay, and the summation theory tells me if I don't find a solution of this form, there does not exist a solution. So this is really an existence proof. So a constructive version to verify if there exists a solution, yes or no. Constructive version. So now we make this ansatz and we plug it in our difference equation. Okay, I just plug it in. Now I use the property of the automorphism, so I can pull over the automorphism to that. I keep this unfixed. I am not, in the moment I keep this here. I can pull over this. I can pull over that, and now I see sigma of s, well, this is s plus 1 over x plus 1. Okay? Just applying the automorphism. And now I do coefficient comparison. And I do it, you see I have here on the left-hand side, the degree is 2 in the ansatz. On the right-hand side, it's 1. So I make coefficient comparison with respect to s to 2. And I get this constraint, sigma of G2 minus G2 equals 0. doing coefficient comparison. Again, I know the constants are just the rational numbers. Therefore, G2 is a constant. I don't know which one, but it's a rational number. So I call this now C because it tells me it's a constant. It's an unknown, but I know I have some information. It's a constant. I plug it back. Since this is a constant, I can evaluate it. Sigma of C is C. And by construction now, left-hand side and right-hand side with the power s squared is gone. S squared removes. So I bring this on the other side. And I get this constraint. I just bring this, not completely determined, but with at least some information, the C, I bring on the other side. And now observe I have done a degree reduction. Here the problem was an equation of degree 2, and now I reduced it to degree 1. So it's a simplification. And now I repeat. I do coefficient comparison with respect to S itself. I get that constraint. In this case, I find the solution G1 with an unknown D, and it turns out C is 0. This is the only solution. Actually, this means G2 could have been immediately set to 0. The degree bounding was too high. So degree bound 1 would have been enough. But only the algorithm now tells me 2 was too high, B was too high, B equals 1 would be sufficient. I get that. I plug it in, and I get another constraint. I solve it, and I get G0 equals minus x, and D equals 0. So if I put everything, and let me say, first thing, there's a degree reduction, degree 2, degree 1, degree 0. Okay? And here I have a reduction because I go in a lower field. Here I'm in the lower ring. Here I'm in this ring. And now I drop S, and I'm in a smaller ring. So here is a extension reduction, and actually here it's also an extension reduction because degree 0 means and the variable S is gone. Okay? Yes?
Can you explain again how you did that C must be 0?
Well, clearly, so here, this is now a new problem. I have to, well, here we know it's a constant. Here we don't know. So we have to solve, we have to repeat the same method in the ring below. And this is the second comment. Maybe you remember, I already mentioned, I'm interested in this more general problem. Okay? So this is my general key summation problem that I want to solve. And one of the sub-problems of that, maybe I write it down, is sigma g minus g equals C1 F1. You can do it right, CD FD. Find all G and all C1 up to CD in the field of constants such that this holds. This was another problem. And now you see, I managed to do a degree reduction and also a tower reduction, but I have to solve a more general problem. Instead of solving the telescoping problem, I have to solve the parameterized telescoping problem. Okay? This is so the price to reduce it to a simpler ring means you have to solve a slightly more general problem. Okay? Which, by the way, is also good for creative telescoping. So it's a bonus. Telescoping reduces to parameterized telescoping. But believe me, if I do this ansatz for parameterized telescoping, it works same. It's the same idea. Okay? And you see, I do degree reduction, and in the end, I go in a smaller ring, and I repeat. I solve the same problem in a smaller ring and in a smaller ring, and finally, I'm back to the case that this is actually K, if I reduce enough. And then this, if this is K, well, this is 0. If I look for a G, and this is a constant, this is 0, and then this is a linear algebra problem. Okay? So you reduce the whole problem to a linear algebra problem. Okay? And, well, if there are products involved, I haven't shown you that, because then the automorphism might also introduce something like that. If you have that, then you might have something like that in front that you, by the reduction. It might happen, okay? So you have to solve first order parameterized difference equations. And well, if you want to solve parameterized linear difference equations, then actually you have to solve this general problem. If you want to solve this even simpler, eventually you will go to this case, okay? So this is somehow the most general case, and when you go to subcases, you will always enter in this case, somehow. Okay, and in this way, we have a decision procedure to solve, to find solutions in our difference ring by degree reduction, by coefficient comparison, and going stepwise in smaller rings. Okay, so this was a basic idea. Now I want to give some more details. First I want to give, well, there are several generalizations. I want to show you a very useful definition that I work mostly. I start with a constant field. So as I said, I want that the constant field is a field, so I start with a field which is constant, okay? And all elements are kept invariant in this field. Think of the rational numbers, or maybe you are drawing extra variables, maybe also algebraic extensions, like square root of 2 and I, whatever you need. Okay. In this particular instance, as you have seen in all our examples, I introduce a rational function extension, and x is mapped to x plus 1. This is always the same what you have seen so far. If I want, for instance, to introduce k factorial, well, if I shift k plus 1 factorial, it's k plus 1 times k factorial, okay? This is exactly such an A that I sneak in, okay? And more, so I introduce a new variable, and as you have seen yesterday, I prefer to work with Laurent polynomials, so I go to this ring of Laurent polynomials, and then I say sigma of P1 is mapped to x plus 1 times P1, and there's a unique way to do this. There's no other way. If I fix that, everything is set if it should be a ring automorphism, okay? And more generally, well, this can be any rational function, okay, non-zero, with this property. And I have basically introduced a hypergeometric product. It could be k, it could be 2k plus 1, n minus k divided by k plus 1. This it depends what you have in the ground field. Okay? A hypergeometric product. You can introduce a next variable, p2, go to the Laurent polynomial extension, and you say, okay, I extend now, the shift of p2 is a2 times p2, and a2 can be in this Laurent polynomial ring below, but it must be invertible. Otherwise, I could not invert. And I can do this iteratively. So I have, basically, you see, I have here nested products. A product of a product of a product can be, or I just stay in kx, then I have just hypergeometric products. It depends how you want to set it up. Okay, that's products. I need a very special element, which I have also indicated already yesterday. I want, for instance, to model minus 1 to the k. Okay? Minus 1 to the k has a very special property. If you square minus 1 to the k, it's 1. So I introduce a new variable, z, it's a ring, and then I shift z, I get minus z, and I need the extra relation z squared equals 1. Okay? And well, or you go first to the polynomial ring, and then you factor out with the idea z squared minus 1. Okay? Depends how you want to see it. Or it's subject to the relations z squared equals 1, but it's an idea that I factor out actually. And that's now the problematic situation, because at this point, I have now I have z minus 1 times z plus 1. Well, this is z squared minus 1, and that's 0. So I have 0 divisors at this point, okay? Working in this ring, it's not anymore an integrate domain, it's a ring with 0 divisors. And this is reflected also to that relation here that you have seen yesterday. Okay. So I feel somehow I feel unfortunate. So I feel not very happy with this situation. Let's say like that. There are two ways now to follow. You can follow Maike Singer's path that you go to idempotent representations, and also in your talk today I saw idempotent representations when you had this xi function, and then you can go to integral domains. I prefer to stay in this ring of 0 divisors and carry it out carefully. There are two paths how you can go. I follow now this path, and the idempotent representation path I also like, and there is now current work in progress, but in the moment this is implemented in Sigma. Yeah. Yeah. You can have algebraic extensions in the set of constants, but this is a minimal polynomial which is irreducible, and you are in the field case. So you don't have 0 divisors. Yeah, this you can also do. You can take lambda's root of unity. This is now a slight generalization. Alpha is a lambda's root of unity. You extend, and then set to lambda is equal to 1. And then you have again 0 divisors, because 1 minus set times 1 plus set to d minus 1 equals 0, okay? You have again 0 divisors. And this works also, and this is the general case that I'm handling now, okay? Okay. Now, on top of that, for instance, we want to model the harmonic numbers, and you have seen exactly this example throughout my lecture already. More generally, we can have a nested sum, so F1 can be any element, the summand can be any element in the ring below. And I can repeat, I introduce a new variable here, a new polynomial ring extension, and F2 can be again in the ring below, depending on S1 and all the variables below. Or not variables, so this element subject to the relation z squared is 1, for instance. And I can continue. Now, if I see nested sums and products, I can do this automatically. It's so naive. Whenever you see a sum, you take the summand and look how you represent them, and you build up. It's just a rewriting. Together with the boundary condition, the initial value, it's a one-to-one correspondence. There's no news. And this cannot be the final word if I do this. The crucial thing is I can do such constructions such that the set of constants remain unchanged. And I have to explain you how this works. The naive construction is straightforward, but to do that without extending the constant, so whenever you have a constant, it does not depend on C3, S3, S2, S1, Z, of none of the variables. It's just the field where we start. And that's the reason why I can guarantee the field, the set of constants is always a field, because I start with a field and then nothing can happen. Okay? Why I'm so much interested in to have that? First point, as I try to motivate, I can decide if the telescoping problem can be solved, because I need that the constants remain unchanged. Otherwise, game over with degree boundings, denominator boundings. Also with the vector space of parameterized telescoping, if the constants are extended, what is the vector space? This is all not feasible. Okay, constants should remain unchanged, and then I have an algorithm. And more generally, I have an algorithm for parameterized telescoping and higher order, first order, mth order difference equations. The parameterized linear difference equation problem can be solved in this setting, and more generally, even in pi sigma fields. Okay. Before I come to the construction point, I want to emphasize one other important thing, namely crucial equivalent characterizations. The first one is we take the naive construction. then the following statements are equivalent. I succeed not to extend the constant, so the constants remain unchanged. Second property, the difference ring is simple. This means whenever you have an ideal which is closed under the shift, so whenever you take, an ideal, if two elements from the ideal and you add, they must be in an ideal. And if you multiply a ring element from the ideal, it should be in the ideal. And the third property is if you shift an element from the ideal, it should be again in the ideal. And it means simple that there are only two cases. Only the zero ideal or the ring itself. There's nothing in between. Okay? And the third equivalence definition is that there exists an embedding from the difference ring together with the evaluation function that I can construct into the ring of sequences. So let me say this is strongly related to Galois theory of Michael Singer and also by Hardouin. And I exploited, and let me also mention, you have seen here only the shift of x is x plus 1, but this also holds for the mixed case, the hypergeometric, the Q-hypergeometric case, the multi-basic case, the mixed case, and it holds also for nested products, the setting, what you have seen. And this is exactly what we use here. Since this difference ring, the constants remain unchanged, I know that this is really an embedding. It's an injective difference ring homomorphism. So I just have to control that I don't extend constants, and then I know the evaluation function that I have defined induces an injective ring homomorphism. That's a very, very strong statement. So I only have to check constants are not extended, and then automatically this tau is an injection. That's a cool result. And this is the main motivation why I am interested in, besides solving the telescoping problem, that I have this one-to-one correspondence.
Could you give us an example where constants would be added?
Yeah, I will do in a minute. Okay, that's this case. As a consequence, if you start with the rational sequences, you have here this root of unity business, and then you get here nested products and nested sums. These are exactly by definition my evaluation function. Then it follows that all these guys are algebraic independent among each other. The polynomial ring, where we don't have relations, induces that also the sequences have no relations among each other, because it's an injective map. And here's for a typical example. You can consider the harmonic numbers of first kind, second kind, third kind, or something like that. You consider this difference ring. It's an R pi sigma ring. Constants are not extended. One can show this. Therefore, we get an embedding of the polynomial ring into the ring of sequences. And the algebraic independence here as a polynomial ring is implied that also the sequences are algebraic independent among each other. So the sequences can be treated as variables in a polynomial ring. That's a very strong, nice statement, and it allows you to prove algebraic independence of truncated sequences. Okay, now we are ready to show examples soon. So I want to show you how to construct a difference ring, that the constants remain unchanged, and there you will see also a counterexample where it fails. Let's look first at the sum case. The sum case is easier. So I suppose we have constructed already a difference ring where the constants have been done properly. So I know how to do this here. And now let's look at the sum case. How can I step by step introduce sums without extending constants? How does this work? So I take a difference ring. The constants are given. And now I do the naive thing. I join a new variable with this shift operator. The naive way. Take a summand of the field below or ring below and say the shift of S is S plus F. Okay? And then the statement is the constants remain unchanged if and only if I cannot solve the telescoping problem. So if I find a solution of the telescoping problem, then the constants are extended. If I don't find a solution of the telescoping problem, I know the constants are unextended and it's a sigma extension. So basically these are called sigma extensions, sigma for sums. So as I said, there are two cases. Either I prove that there does not exist a telescoping solution, and I can do this with my telescoping algorithm because the ring below I have constructed properly. The constants remain unchanged. I can decide if there exists a G. If I prove there is no G, then I can join a new variable. If I find out there is a G, then actually there is no need for a sigma extension because I can model the operation already in the ring below. So let me show you an example, and it's almost embarrassing, but I show it to you. And it comes from any identity that you have. For instance, look at the Gauss sum. Okay? You all know the Gauss sum. And I could model in two ways in a different ring. I could start with Qx. Okay. And then I join a new variable with sigma of s equals s plus x. And I model basically the sum. If I shift the sum, it's a sum plus n. Okay? Or I can take g equals x minus 1 times x divided by 2. And then I have also sigma g minus g equals x. It's a telescoping solution of the Gauss sum. Or I can write like this. So you see, I find two solutions. And now I can do I show you the extension. I can look at this. S minus g equals S minus g. I take this equation minus that equation. And you see, that's an element which is constant. S minus g is a constant. If I shift s, I get s plus n. And if I shift g, I get g plus n. If I subtract, I get s minus g. Do you agree with that? Or do you miss something? So I just subtract these guys, or maybe let's write it like this. Maybe you see it then better. I have these two equations, and I subtract them, this minus this. And this is s minus g equals s minus g plus x minus x. That's 0. Yeah, so I was asked, can you show me a construction which is stupid? Here's a construction that is stupid. I join a variable s to model the sum, but it turns out I can model the sum behavior already in the ring below. So don't do this. Just take this as my sum solution. Don't introduce a new variable. It's like you have a polynomial and you have a root. If you get the root already in the field of the coefficients, you take this, you don't say root of. This is stupid. You just take the element in the field below and say, this is my root. It's the same thing. You don't need root of. This would be statement root of, there's a new algebraic extension. Then you need an irreducible polynomial to introduce it. And I can do this basically iteratively. I always try to set telescope. If I can telescope, I can simplify my sum in the ring below. And if I fail, I join a new variable. I do this iteratively. Okay, and let me make this clear now. This is basically the naive ansatz by Michael Carr. Given a pi sigma ring or pi sigma field in Carr setting, you're given a field, find in case of existence such a solution. And there's an algorithm done by Michael Carr and slightly generalized in the ring setting. Still naive, I allow also root of unities. Of course, then I have to go to rings because I have 0 divisors. It's still naive. The crucial thing is, I can only simplify sums as well as I have constructed the ring below in a nice way. If the ring below is bad, I cannot expect to get nice solutions that in which I want to solve. So one has to design an appropriate R pi sigma ring in order to find, or in order to solve the problem in the ring itself, or to construct an appropriate extension such that you have simplification. And appropriate means, for instance, that you have here the sum, that actually this would be a sigma extension. I cannot solve the problem in the ring using the harmonic numbers and the harmonic numbers of third kind. I cannot do this. So I could extend now this as a new sum. This would be a sigma extension. Or I do better, I introduce the harmonic numbers of second kind, and then basically I can express this as what I can pull out, and I get rid of these nasty denominators. Okay. So I think we all agree that this sum extension is ugly, and that is a nice sum extension, okay, to represent the same object. And similarly, I worked on reducing the nesting depths. So look, for instance, at the sum of a sum of a sum. It has depth 3 summation quantifiers. And if you look naively, you would say, okay, this is a sigma extension. Then the next sum is also a sigma extension. And the last sum is also a sigma extension. So I introduce 3 variables, and the second variable depends on the first one. And the third variable depends on the second one, which depends on the first one. So I have a nested extension. Okay? Alternatively, I can write this sum as the harmonic numbers of first kind, second kind, and third kind. These are also sigma extensions, namely the harmonic numbers of first kind, second kind, third kind, but they don't depend on each other. They always depend only on the field below. They have nested depth 1. And the 2 difference fields, rings that I construct, are isomorphic. They are the same up to renaming. So from the difference ring setting, it's nothing new. But from the representation point of view, that they're less nested, it's a new ingredient. So simplification means something new, not only a difference ring, which is isomorphic or contained, but you need extra simplification properties to specify what means simpler. And let me show you some examples. Okay, let's go here. This is a typical example of, I don't know, a 1, 2, 3, 4, 5-fold sum. And if you apply sigma reduce, you can flatten the sums. Okay? By some extension, so iteratively extend the difference ring, and I get a nice difference ring extension, not a naive one. Or here's the opposite. Imagine I have already joined a difference ring where I put this sum and then this sum, and they are sigma extensions. And this is now my tower that I suppose is granted. And now I want to simplify that sum. If I do that, and I do it naively, then you see a single nested sum is simplified to a single nested sum plus a double nested sum. So if you do the construction in the beginning wrong, the output cannot be good usually. Okay, so one has to be very careful how you design the difference ring in which you want to solve. And this has to be done very, very careful. So for instance, here is a situation where I managed to flatten a triple sum by a double sum, but I don't introduce here one single sum, but I introduce a sum of a sum. So I have sometimes to introduce more summation. So you see here, this is 1, 2, 3, 4, 5 sums, where here I have only 3. So sometimes I go in a larger ring to flatten. Then the transcendental degree is larger. But the flattening is correct. And I can guarantee when later I introduce sums, I can always find the optimal nesting depths. So I have somehow, I look in the future, I extend in such a way that when something new comes, it can never spoil later the degree, the extension degree in the depth. Okay. Here's also another example, interesting. So you see here, we have here a sum, and I managed to get rid of the harmonic number. So I introduce a summation quantifier, but I managed to eliminate the harmonic numbers variable. And let me just mention, this is also interesting for, there are other examples, maybe I skip. Also interesting for the whole thing what I showed you for telescoping also works for creative telescoping. So for instance, I can compute a recurrence for that sum. It's a recurrence of order 3 using creative telescoping. Or I can extend the different rings. We discussed this, I think, also yesterday. I can introduce some extensions which are free of the harmonic numbers, and then I get a recurrence of order 1. Of course, now you get here somehow definite sums because you evaluate at the upper bound minus the lower bound. So you have to do something on the hypergeometric level to simplify, but then you have to solve a recurrence which is simpler. So this can be expressed by something like 2 to n and some variations. It's a binomial theorem somehow. And then you have to solve only a first order recurrence, which is much simpler than higher order. Okay. Here's another example. It's a double sum, and then here binomial coefficient. If you do it naively, you get a recurrence of order 4. Or if you extend the difference ring in which I solve, I can express it again by sums, which are now simpler. So instead of a double sum, I have only single sums involved. So, and there's a trade-off. Sometimes it's good to do extension, sometimes it's not so good to extend. So it depends on your application. I want to quickly show you the product case. So how can we automatically extend products? And here, same thing. I naively adjoin a new variable. I go to the Laurent polynomial ring. I introduce this naive shift behavior. And then there is the following hope, but unfortunately it's not as simple. The constants remain unchanged if and only if there does not exist a solution of the multiplication problem. This would go exactly like summation. If I succeed to find a solution, hooray, I can express it in the ring below. If I fail, I join a new variable. But unfortunately, this is not the case. The situation is there does not exist a g, and there does not exist an integer, not being 0, such that I can also raise the multiplicand by a certain power. This gives an extra complication. Only if this is the case, I know it's a pi extension. And there are now 3 cases. This criterion is satisfied. I don't find a g and a n with this property. Then I can join a variable. I'm done. There's the case that I find g's which exactly models the shift behavior of a product. I'm also done. But there might be also the case that I find something, but only if I raise it to a certain power, but not for n equals 1. And maybe I can show you here a quick example. Example, for instance, I start with q. I join a new variable, and I say, for instance, sigma p equals p times 4. So this represents basically the object 4 to n. I shift 4 to n, I get 4 times 4 to n. Okay? So I suppose I have constructed that, and now I want to model 2 to n. Okay? So okay, I could introduce a new variable. The sigma q equals 2q. But you see now I have a problem. I can now take mp divided by q squared and shift it. This is p divided by q squared. this power to 2 is a spoiler. And I cannot take root of. I cannot take root of a rational, of a variable. This is not allowed in a rational function field. And this is exactly the problem. I find sigma g equals 2 squared times g, namely g equals p squared. So the spoiler is I can raise the multiplicand by a certain power and can solve the problem. Now you can say, okay, I should have used first this guy. I should have modeled first this. And afterwards, I should have modeled that. I could redesign now my whole difference ring to make it possible. Okay? But there are other situations where you cannot do it so nicely. So in the worst case is -1 to the n. -1 to the n you cannot adjoin as a pi extension because there is a solution sigma of 1 equals -1 squared times 1. Pi extension, okay? But there's a way out. There are two ways. So, and this is basically the slide that you have seen. So I'm given, for instance, the rational functions here. This is my standard shift operation. I take multiplicands a1, a2, up to ae. And then I can define a difference ring such that I can model the shifts. And it's an R pi sigma ring. And I can do it in such a way that I introduce pi extensions, only pi extensions, and one root of unity extension. So one root of unity extension is sufficient to tackle all the bad guys. And similar results for the Q rational case, multi-basic case, and the mixed case. So this also holds there. And there are two variants how I can do this. Consider, for instance, these 4 hypergeometric products. Okay. Then I can represent them in the following difference ring, namely by n factorial, 2 to n, 3 to n, and I to n. And you see basically I hack it into atomics. I take the integers and I allow only if I take a rational number, I factorize it in prime numbers and I take the prime numbers. These are the atomics. And I take, for instance, k and not 1k, and then k plus 1 can be mapped to k. So k factorial is sufficient to do the step. And I have to do here I to n, you see it from here, it's in here, to model that. So I find an R pi extension where these elements are transcendental and I to n is algebraic. And the idea is hack it into atomics in building blocks that cannot be split further, and then I can guarantee whenever I extend later, it works nicely. The other example is, same example, that I take this product, that product, and -1 to the n. Then I can again write these guys, y1, y2, y3, y4, by these 4 guys. The difference is I have only 2 extensions instead of 3. And I have -1 to the n instead of I to n. So I have minimized the transcendental degree and the order of the root of unity. The disadvantage is, so the Smith normal form is in the background to do this calculation. The disadvantage is if later products pop up, I might have to redesign the whole thing to make it work again. Whereas in this example, these are atomics, I am extension stable. Whatever comes later, I can guarantee that I can express it in the ring below. So there are advantages, disadvantages. Okay, and this is now basically the full machinery given an expression in terms of indefinite nested sums and products. Sigma reduce actually delivers another representation such that A equals B, and I have a delta from this point on, I can guarantee there are no poles. So I know from this point on, my representation agrees. Further, the rising sums and products are algebraic independent as sequences because I have this, I take care that the constants remain unchanged. And second, I have all the simplifications of flattening and reducing the depth or something like that. This is all encoded in sigma reduce. And what does it mean? Usually I can find a lot of relations and the expression collapse, gets simpler. Second, I have the zero recognition problem. An expression is zero if and only if the output is zero. And as we have seen, it follows your definition, I have canonical form representations. Okay? And what I've mentioned here works also here. I construct a different string for my parameterized telescoping problem, and I solve it. I solve indefinite nested sums in this D'Alembertian solutions, and I reduce the nested depths, and I find all algebraic relations among the objects. I find always the optimal representation. And I know I'm almost too late, but I want to show you one example of sigma reduce. Here are two expressions, A1 and A2. A1 equals A2. At one point, I think you can already believe that it's true, but they look completely different, right? Now I can make sigma reduce of A1 minus A2, and it's 0. So I have a proof that the two sequences are really equal for all n. But here basically I put all the sums in one tower. So these are all objects that you see. This is A2, and these are the objects of A1, okay? And if I apply now sigma reduce, it doesn't collapse, but I find all the relations. So you see, if I do that, well, n is mapped to n, and in this order, the tower was built, because I get it in this way, okay? And you see, suddenly we get relations. This sum can be introduced by these sums that I have already put in my tower. So you find identities and relations. And the funny thing is that sum and this representation are the same, so they collapse in this representation. So I can hunt for algebraic relations, and I have also proof that these relations, there are no relations among the basis elements that you see on the right-hand side. These are all algebraic independent among each other. So this is a strong tool to prove algebraic independence of truncated sequences evaluations. Not theta 2, theta 3, these are infinite objects. This is a different story. And with that, I would like to stop. Thanks.